Okay. That's on.
Should we just go without it?
Sure.
All right.
Okay. Hello, everyone. Sorry for the slight delay. We're gonna get started now. So my name is Aniket,
My name is Umer.
and we are from ECLAIR, which is the engineering and computational learning of AI and robotics. It's one of the largest AI and it's the largest AI and robotics org on campus. And today we're proud to present a small workshop we have put together on AI and LLMs, specifically on implementing them in hackathons. So yeah, come on in. We're just getting started. So we're going to start off with a small intro to large language models. And the first thing we're going to do is Umer's going to dive into a short introduction on what transformers are. I think everyone has heard of the attention is all you need paper, pretty famous seminal paper that came out with the transformer architecture in 2017. And that's been the driving force behind a lot of, it's a driving force behind large language models and other kind of models. And Umer will dive deeper into that right now.
Right. So first, I want to kind of get a basis of where we are in understanding. So are you guys familiar with the encoder-decoder structure of GPT models? All right. Okay. So I'm gonna take that as a no. But okay. So basically, you can essentially formalize these LLMs into two major components: an encoder section and a decoder section. The encoder section is primarily for taking text and essentially. You can basically think of it converting it into machine thought, where basically we can get LLMs and maybe other type of neural networks to understand what text is actually representing. So if you hit the next slide. So we can see here the general structure of the encoder-decoder structure. And here, basically, we're seeing how it's structured for LLMs. The two major things we need to focus on is the positional encoding structure as well as the multi-head attention loops. So essentially how these are structured is that you guys understand how how embeddings work from going from single tokens to vector representations? Okay, so essentially how BERT is trained is that it trains on three major features, right? So given a sequence of text, it will essentially mask some of the text inside of the string and will have to determine what those texts are for training. It will also then take two sequences of, or two sentences, and we'll try to determine which one came first, right? So in terms of, those are the two major structures in which encoders are trained. Now, for decoders, you simply have to use the transformer architecture to essentially take the positional encoding, which basically tells you where it is inside the sentence, and essentially create a distribution in which it will believe the next generative token will be. All right.
Yeah, next slide. Oh, so just before we dive into that, everyone's heard of ChatGPT. It's the public interface behind the GPT model from OpenAI. And GPT essentially stands for Generative, Pre-trained, and Transformer. Umer already explained a lot about how transformers work with the encoder and decoder network. What generative stands for is that the model guesses the next word, and pre-trained is that it's on a large document corpus. We'll see how these two tie in downstream in a few slides. But basically, some prevalent LLMs today are, of course, OpenAI's 4 series, the 4 and the 4 mini, as well as some by Claude, Gemini by Google, and by Llama. Llama, yes. So how does an LLM choose the next word? Now, this is obviously highly simplified, but what happens is that you have a string of input text. In this case, in this example, it's Paris is the city. That is runs for tokenizer. Basically, each word is treated as a token, as one single unit. A token is the smallest unit of operation for an LLM. And then each token, each word is assigned a token ID, which you can think of as a unique ID to that token. And it's fed into the large language model. And that basically computes the probability of what the next word is going to be. Paris is the city. After that, based on these token IDs, it can say that the next token ID that corresponds to off has a probability of 33.7%. Then after that, that might be 15%, where 0.09%, and so on. So essentially what it's doing is that based on a stream of input text and those tokens, you are computing the probability of the next word from an entire list of possible words, and it chooses what the most likely next word is going to be. So I have a question for you. Based on this overarching model of how an LLM works, do you think an LLM actually thinks? No? Yes? And does anyone want to explain maybe? Okay. So as I said before, the LLM is generative. It just computes the probability of the next token. If you look at that GIF over there, which my face is covering, it's essentially just putting one track after the next track after the next track. This is how an LLM just chooses one token after the other to do so. And as I said, it was pre-trained, so it has a huge training corpus that's of the entirety of the internet with research papers, textbooks, news articles, novels, etc. And if you think about it, these are very rigorous, highly vetted sources, and you can think of how this might impact the LLM functions, and that's going to be factored into the pros and cons for that. Let's see. So yeah, with the pros and cons, this point about how an LLM is generative is both a pro and a con. For example, since it just computes the probability of the next word, it doesn't have a lot of correctness criteria built in. Now, ChatGPT does, because that's a public interface. And so OpenAI has a lot of rules-based post-processing that happens on the model output. But just the raw model can and quite often generates fake or incorrect data. And it sounds real. It says that with authority, because since it was trained on highly authoritative sources like research papers or textbooks, it knows how to craft a sentence so that it sounds real. So that is one thing you're gonna have to watch out for when working with LLMs, is that they can often hallucinate or make up incorrect data that sounds real. But then the opposite of that is that since during the training process, it's had access to such a wide variety of sources, it can generate hyper-realistic data, which is basically data that mimics reality. And that's actually a fake data, but you can use it in lieu of real data. For example, if you're building an LLM solution and you need access to, say, leases, accounting data, or graphs, or things like that, these kinds of sources are something companies and industry partners hold very closely to themselves. They don't like releasing it. So if you're ever functioning, but you need those to actually build out your LLM app. So you could work on generating synthetic data, which mimics it. If you've seen like lorem ipsum, it's kind of an extension of that kind of mock text, but it has realistic sounding words in that. And that can basically, you can use that as your input data set for the LLM app. And I think that's one pro tip that you should probably try to work with, using LLMs to generate synthetic data, and then further feeding that into your LLM app, especially for a hackathon standpoint, where you have such less time to actually find training data. So if you want to get documents or a large corpus as your input to an LLM app, then that's a pro tip. But yep.
It seems finished. Can you go back to slide?
Oh, sure.
All right, can you finish the thought?
Oh, yeah. So basically, large language models are large in the sense that they can generate text for any situation, but they only generate text, and it's up to you to learn how to use them correctly and appropriately.
So also one question you may be having is, when we said that we were using token IDs, you may be wondering how, since we're using this distribution, we're simply choosing the largest one, how ChatGPT is able to respond differently for each prompt. Well, the main way it's able to handle that is something called temperature, where essentially it won't always choose the top prompt, but it may instead choose something of a lower distribution, right? So basically, you can think of it as higher the temperature, the more random the selection it will be. Also, you may be wondering, even though these LLMs are decomposing the knowledge like this, how is it able to look at words with different meanings in different contexts? The main way we can do, one thing I want to make clear is that token IDs are not simply just a dictionary of just one word or one token. It just corresponds to one ID. Multiple tokens can represent different IDs depending on the context it's already seen. So and these tokens are not, or these basically these vectors are not just random sequences of numbers, but are instead semantically related to each other. So basically, words that are very similar, like for example, let's say city is the one that got this token right here. Instead of 171, if we made it like 170 or 169, it would maybe something that's very similar in idea, like maybe like a town or like a metropolis or something like that.
Mm-hmm.
And so you can essentially think of these IDs or each number in the ID as kind of as a dimension, which kind of describes how well a word fits in that dimension. So, for example, a very common showing of this is that if you take the token king and you take the vector that it spits out from the tokenizer and you subtract the man token and then add the woman token, you'll actually get the token ID that relates to the token queen. And so essentially you can think of it as LLMs learning not only just the contents of it, but the actual contextual understanding of the document itself.
Ooh. Okay.
All right, so we're going to move on. Do you want to go on to demo then?
Sure.
All right, so we're going to move on to a demo of using.
So basically, what prompt engineering is how you specify instructions to the large language models. How you can think of this is that since large language models are so large, you need to constrain them down to what you're trying to work with. And the prompt is essentially the way you instruct the LLM. Now, there are multiple types of prompt engineering. Like there's zero-shot learning, multi-shot learning, etc. Zero-shot just means that you tell it what to do without any examples. Few-shot is that you provide some examples to it. But one really popular and I want to say effective method of prompt engineering is agentic prompting, where you essentially ascribe a role to the LLM, and it through its training, it has learned the different functionality of that role, and it sort of inherits from that. A more concrete example can be telling the LLM, you are the head chef for a restaurant. Based on your knowledge, craft a dinner menu of a French cuisine that's in this high-end location, etc. So through its training data set, it has learned what the functions and what a human would do in that role, and it can sort of use that in user general context to be more effective when outputting instructions. Yeah, and I'm going to sort of demo how all of these work. Two main things. A very popular library or framework for working with LLMs is LangChain, which I think if you are building something large language model related, everyone should learn or at least know. That's what I'm going to be demoing. And then depending on time, I'm also going to dive into retrieval augmented generation, or RAG, which is basically using the LLM to query a database and pull out chunks from that. Let's see. I'm gonna pause sharing for just a second. Oh, is it still? It says paused.
Just gonna take off the HDMI, right?
No,
Yeah,
it's fine.
I mean, it's still gonna, switch off the screen.
Oh, really?
Yeah.
Who cares?
All right.
Let me just move this over here. Oh boy. Excuse me. Okay, now it's here. Share screen. Okay, so the recording is still on. Okay. So the way you use LangChain to essentially how you wrap the API call to okay, let me preface this. I'm working with OpenAI's GPT-4 model, and LangChain is the general library through which you can yeah. So LangChain is a library through which you can essentially work with these models, the raw models, the output of the API calls. And LangChain operates in runnable units. This is essentially to create the chain. And an LLM chain is a runnable pass-through chain, an object which takes in runnable Lambda objects. And the way you use these runnable Lambda objects is simply chaining together whatever you want to pass through the chain. So let's see, in my create chain function. Oh, another thing, whenever you are working with LLMs, you're going to send them messages. That's the way you essentially send your query and get back the response. I'm assuming everyone has used ChatGPT over here. That's literally what you do. When you type in something, that does send as a message, and then whatever the LLM sends back is stored as the LLM's message. And since there's a unique session ID related to each conversation you have with the large language model, that basically allows it to look over the conversation history and extract more context from that. But oh, and this temperature that Umar mentioned is again, temperature is a way to determine the level of creativity of the model. Over here, we're using 0.4, which is slightly on the low side. It goes from 0 to 1. So if you wanted to be more creative or more diverse with its outputs, you can crank it up to 0.8, 0.9. If you want to be a little bit more deterministic with it, you want to get sort of the same professional looking text all the time, you can make that 0.1 or 0.2. So here, I'm assigning, this is something just standard. You just pass in the start time. But this is what the money equation, the money part of the code is going to be. You assign the prompt, and if you want to pass in a function, you just wrap that into a runnable Lambda. Like over here, I have this debug print and return, which really prints out the data. You wrap that in a runnable Lambda call, and then you send it. And then this model, which is our API call over here, and then a string output parser just to stream out the text. And this creates your chain. Now, how would we want to prompt this? Let's say, oh, and for some background, what I'm trying to build here is essentially an interface which can take in a few details about say a lease. So it takes in the tenant name, the start date, the duration, the price per square feet, etc. And I have an example PDF right here. Now this was also synthetically generated. You can again see the power of synthetic generation in this case. This is all fake. Someone else is currently residing at Broadway, 123 Broadway, New York. But basically, I passed in a bunch of context to ChatGPT, and using agentic prompting, I said, you are a lawyer who specializes in building contracts. Here are the details. Ensure that these details are enforced throughout the contract, and then used it to essentially create this lease as markdown text and converted that back to a PDF for display over here. So you can see some things like tenant responsibilities, utilities and services. I did not tell the LLM to include these, but since through its training data set, it knows that leases generally include these kinds of clauses, and it inserted those into the example PDF that I have right here. And that's what we're gonna be working with. So here, I basically format some input parameters as I want them. This is just trivially a string input. And then passing in an example PDF. This was not working unfortunately 10 minutes ago, which is why there was a slight delay, but we'll see how much it works. So you get this, you create an object or the lease chain, and you run the create chain function, which basically creates this runnable serializable object from this from the entirety of this runnable pass-through. You basically take all the runnable lambda objects, put them into runnable pass-through, and that's your serializable chain. And now let's prompt this. You are in. Do you have any ideas behind the prompt engineering?
Because then,
Drafting. Drafting commercial lease agreements. Based on the details of the client, such as the name. Well, maybe let's just close the tab on over here. Let's tailor to their needs. This is good. An example of data is the same throughout the document. Now, why did I add this? Just to ensure that we do not have hallucinations in this case. Ensure the data is the same. Maybe you can make this a bit more realistic. The same means the same throughout the case. Okay. And let's pass in. This is going to be our example PDF. Not over here, over here. Mhm.
so I guess we're fixing a couple bugs. So I just want to preface again, the main power that comes from chaining together prompts is that the input from one, or sorry, the output of one becomes the input for the next frame, or for the next thing in the chain, which is extremely helpful because you can start taking inputs from different APIs as well, right? So you can take, maybe information from a Stripe API caller, or maybe a Gmail call, and essentially have your LLM be able to perform certain actions based off of the output seen from those API calls. And LangChain itself actually comes with a lot of pre-built tools that can essentially handle formatting the data as we're doing now, where instead of creating it yourself, you can actually use pre-made tools to handle different tools as well as looking for certain through certain documents.
Oh,
Right. So basically, okay, as continuing, so right now we have a very well predefined chain where essentially it will go from top to bottom, going through each element in the chain. However, LangChain is powerful enough to essentially use something called agents. The main difference between chains and agents is that an agent will actually select which how it will flow through the chain, right? So right now we're specifically defining, taking in this user prompt and then looking through the document, but through an agent, you would simply provide it with all the tools that you need to essentially essentially to perform any action you would want it to, and it could define the chain that the LLM could define the chain that it would want to run.
interesting. Model not found. That is perplexing. But I think everyone gets what the point of this is over here. You are essentially creating the large language model chain, chaining together all the parts of it, the model itself, the prompt, and the some functions. You can add custom functions over here. This is helpful for adding function calls in your code to basically further work on the data and do some more processing. And then this chain is returned. And then in the runner over here, you create the chain and then it's invoked. And then this result content is going to be JSON / kind of like an object. And that you pull out the content, which is going to be a text-based field, and you can work with that further. Say this works. Okay. Now let's say, now I'm just gonna code up. I won't run any further code because this is breaking for some reason, but I'll just show you how you can work a little bit with RAG. So the first step in that case is going to be chunking up the documents. So you're going to start off. One library I like to use is unstructured, which easily adapts to various kinds of file formatting and takes it and divides it up into chunks. These chunks are going to be stored as LangChain documents. So each chunk can operate as one document. And then you take that, and then we create a collection in a vector database. A vector database is essentially like a repository of all the chunks with the embeddings. And again, Umar talks a little bit about embeddings and how they work. You take the text and convert it to a vector representation. And then you can essentially query those and run an LLM chain, which basically looks at them, selects, let's say n chunks with which map to that embedding, and then pull out the relevant ones. So let's say you run a partitioner, chunks.
So as Enki is coding this, I'll give like a brief overview of some pulling from vector database strategies. Now, obviously, you don't want to pull it from just one chunk to determine what you want to do with your output. It makes a lot more sense to pull from multiple chunks to make sure the data you're seeing is correct. Now, one issue that you may have if you just try to take the most similar vector is that a lot of documents will be very, very similar to each other, which may result in very either skewed or biased data that just simply tries to mimic what the prompt was asking for. So one thing we actually do is something called
Max marginal relevancy search?
Yeah, so max marginal relevancy search, which essentially makes sure that the uh, chunks that were pulled are not related to each other, but are also related to the prompt that was given. And typically for finding which chunks are similar, you can use a very common popular strategy is simply taking the cosine similarity between the two vectors. Basically, the smaller the cosine value is, the more highly related the documents are. Let's see.
Oh, no, you can keep talking.
So there are also other major facets of LangChain that are useful for working with LLMs. Obviously, the way how LangChain is structured is that it's very easy to replace which model that is being used. So, for example, if we wanted to switch from Ford to maybe something like Olama, we would simply need to change the actual model attribute, and we could simply leave the remaining code unchanged. The second is, as we were saying before, as we have a very formalized way of representing prompts. And one thing that is certainly important for, maybe for a conversational bot is having some form of memory, right? So right now, if you were to simply just run this over and over again, it wouldn't contain the memory of all the previous conversations it would see. But through the memory module inside LangChain, we're actually able to remember previous conversations that we had. And we've already talked about both chains and agents, but just as a quick overview, chains are very useful for when you have a certain sequence of instructions that you want the LLM to go through to handle one specific task. And where agents instead simply have access to the tools that you wanted to interface with, and it can choose how it wants to how it wants us basically answer the prompt with the tools provided. Yep. Okay. This was going to, I'll show you, we can see it.
Is your thing rolling?
Sorry,
What was that?
I'm just looking notes.
Okay. Oh, yeah, let me just show you the.
All right, so right now, do you guys have any like major questions you want answered about either LLMs or maybe AI in general?
Yeah, okay. So basically, I want to show you the code because I'm not allowed to because it's from my workplace. But essentially, how you would set up a rack system is you would take those chunks, you would set up a quadrant collection, convert those chunks to embeddings, then insert those documents as embeddings into the quadrant collection. So now once that's populated, you would set up a chain similar to how I showed you, same structure. It can be called chat chain or something else. And then you would invoke it by sending a query. And that query would just be a question. And the configurable in that case would just be the session ID. There can be a UID if you want to every time, or it can be a set one if you want to, maintain the conversation history. But what that basically will do is that inside the chain, you would look at you would have a search query that will look at the chunks and then run. You would do runnable lambda on basically doing on the vector store. You would run max marginal relevancy search, which is what Umar mentioned. How you're gonna get sort of diversity between those chunks, and then you can fetch a larger number and then choose a smaller number out of that and filter them through, and that's how you would get your chunks. And then how RAG works is basically selecting the first n chunks that fit your criteria. It's not going to be exhaustive. Let's say you wanted a list of 10 pieces of data, but they're all chunked up into, say, 4 chunks, then you might get the first 3 chunks and not the 4th chunk. That's something you might want to look out for. There's something else you can do in that case, which is function calls and iterate through the entirety of the vector store and get the relevant pieces. And there's a lot of literature on there. The point of this workshop was essentially to be an introduction. Again, LangChain and other LLM providers and service maintainers have a lot of good documentation and open source documentation that you can reference. And of course, you can use ChatGPT and Cursor and other AI tools to help you while coding. So as long as you have a good design in mind with the architecture of how you want your app to look, given today's like ChatGPT support while coding, it shouldn't be too much of an issue. Just make sure that if you're getting bugs, look at the documentation, because one common bug is if you misselect the cleanup mode, cleanup is essentially whenever you insert a document, you can either clean it up fully or incrementally. What that means is that if you do all the existing documents in the one collection will be destroyed, and then you will import ingest the new documents, or incremental is that you just replace the chunks that have changed. And there are use cases for both of them. Just make sure you're choosing the correct hyperparameters and just calling the functions correctly, and you should be good to go.
So we'll open the last 10 minutes for any questions about like either AI in general, LLMs, or LangChain itself. All right.
Yeah.
There's a specific reason why a lot of language models use Python.
Yeah, so the main reason why most interface with Python is simply that it's a very, very simple, or it's very simple language to work with. There is no specific there's no reason why you couldn't code either an ML model in like C or Rust or something like that. But it's just that with Python, it typically helps with especially with large library that already exists like NumPy and Lightning Torch, where it's very, very simple to create on top of those libraries instead of having to create it through something like C or something like Rust.
Yeah. Also, Python is very easy to write, and given the modern state of it, a lot of the development actually happened in Python. Again, as Umar was saying, all the libraries that are the most powerful today work in Python, like LangChain, for example, or other, like you have Langsmith, LangFuse. A lot of the LLM app development is also done in Python, and that's it's actually really easy from an implementation standpoint, because you can just create the backend in Python and then hook it up to whatever front end that you want in React or Next.js, etc. Yeah.
All right, guys. Hope you had a great time at that workshop. We have workshop raffle tickets for you. So at the exit, we're gonna be giving you like a little red raffle ticket. You can go to the front desk anytime today, before like 8 p.m. and you could spin a roll on the gotcha machine. You can get a little prize from it.
Okay. Thank you so much.